Hello everyone, welcome to ScyllaDB Summit 2024. My name is Srinivas. I am co-presenting with Jives on the topic tracking millions of heartbeat on G's OTT platform. From this presentation, you will get to know how we have won the hearts of our customers. Let me begin with a short introduction to us and our company. About G5, one of the leading India-based OTT platform with several millions of viewers around the globe and over 500,000 hours of content and 100 billion plus app downloads. About myself, I am a principal architect in G5 with experience of building large-scale software system. I have got 20 plus years of IT industry experience, and my previous company was Charmboard. I built video discovery and commerce product from the scratch for OTT platform. So this agenda of this overall presentation is going to be an heartbeat architecture design and metadata management, continue watch feature, and concurrent viewership count. So I'll be mostly covering up architecture design, and low level design will be covered by Juves. A term heartbeat in this topic is a request fired at a regular intervals during video playback. This presentation covers how we leverage heartbeat data to rebuild continue watch and viewership count feature with the help of ScyllaDB capabilities at P99 single digit latency. So let me move to high level design. So these are the list of the architectural goals that we had for taking the decision to re-architect this overall heartbeat system. So one is like to remove the dependency of cloud vendor specific architecture so that we don't need to depend on cloud native services. And another factor is the cost optimization, and it should be open source so that we can deploy it in any cloud provider, and we can natively run it in the background of any infra, and high throughput and low latency. And we expect less than single digit latency is one of the criteria for re-architecting this whole heartbeat system, and it should be multi-tenant ready so that this software can be reused for any OTT providers and easier to ship and launch new use cases so that we can extend to any kind of use cases so that without making any big changes in our architecture. So some of the examples are inserting the new episode in continue watch rail and concurrent viewership count. So we have evaluated multiple databases like Redis, ScyllaDB, Cassandra, and Apache Ignite. And finally, we have opted for ScyllaDB due to this for these below reasons listed in the bullet points. So reason why we have opted for ScyllaDB is it is persistent and in-memory DB. So we no need to have extra cache layer on top of the persistent DB so that ScyllaDB can manage both cache layer and persistent DB within this infra, and it contains low latency across the region and replication and multi-cloud ready. It can work in any cloud vendors like Azure, AWS, and GCP, and they provide managed support with the turnaround time of within less than 1 hour. So that's why we have opted for ScyllaDB. This is the old architecture where it explains about cloud native, how we have built heartbeat architecture in cloud vendor specific platform. If you look into this diagram, we have used multiple DBs. We have used DynamoDB to store heartbeat data, and we have used RDS to store next and previous episode. We have used Solar to store persistent metadata, and we used Redis to store cache of the metadata, and we use another Redis for to store viewership count details. So in our new architecture, we have simplified and flattened this architecture so that all the heartbeat system will be pushed into our heartbeat topic and get processed through the stream processing and then ingested to the ScyllaDB cloud with the help of ScyllaDB connectors. At other end, we have CMS layer where whenever content get published, so that it will be ingested to our metadata topic, and then it gets inserted to ScyllaDB cloud with the help of metadata connectors. So with this new architecture, we have we have almost managed to convert the DynamoDB RDS Redis Solar workload to ScyllaDB. That saves us 5x of cost, from $62,000 to monthly cost around $12,000. From this slide, I'm going to end and give my control back to my colleague Jivesh, so that he will explain low level design of this.
Hello all, I am Jivesh Sareja, tech lead at Z. I love to work on complex use cases and design and build them. So I have around 8+ years of technical expertise in DRM contents, blockchain technologies, and stream processing. I worked in companies like Wipro, Nagra, Kudelski, and one of the blockchain companies at ChainThat. So I am the key developer who was responsible for redesigning and redeveloping the entire heartbeat system for Z5. Okay, so I'll be taking over you all over through some insights on the low level design, some learnings, and some problems which we faced during this and how we could overcome them. Okay, so the next slide you see is our real-time stream processing pipeline. Okay, so as Srinivas told you that heartbeats are being fired to Z5 at regular intervals. So we have a 60-second heartbeat time. So every front ends, whenever a user is watching a video, so every 60 seconds a heartbeat is being fired, which passes through our playback stream processing. Okay, and then through some business logic consumers into the data form we want, it's processed and kept into ScyllaDB. So this is our overview of the data ingestion pipeline, which is handling the millions of requests. So the next slide you see is our scalable API layer. So first comes our heartbeat service, which is responsible for the loads and loads of data ingestion, which is processed into a topic, and through the topic it's processed, and then through a connector it's processed and kept into ScyllaDB. The other services are the get your continue watching rail service and the delete from continue watching service, and the resume playback service, which helps you to continue from where you had left off. And then we have the concurrent viewership count, which leverages the Scylla to get ScyllaDB to get the concurrent viewership count per user or per asset, so per ID. So let's say you release a movie and I want to know how many users are watching this movie today at this moment. So it's I will tell you how we could achieve this use case through Scylla. Okay, so I'll move over, and this, as we promised, that first use case which we solved was metadata use case. So as Srinivas told you that we were using three DBs, three things: Solar, Redis, and like Postgres to manage such a large metadata in our OTT platform. So this is the first challenge which we solved, and we strategically designed our data model into ScyllaDB. And through the ID partition key, we were able to, and some materialized views, of course, we were able to solve use cases like metadata insertion, and we were able to get the move out from Redis and Solar into Scylla. So we could achieve just all these use cases in Scylla. So the next slide gives you some insights on the metadata model. So as you see, like it's a metadata, and we have ID as a partition key. So this table, I would say, had lesser writes. So like you can say only some writes whenever a new asset is being released, we write into this, and more reads. So we used level compaction strategy here, and choosing the right keys, like right partition keys, and the right clustering keys for our views helped us to get a single digit millisecond latency in this model. So the next use case, what we solved is the continue watching use case. Okay. So let's say what the user expects. What you expect? You're watching a content on your Android phone or a iOS phone, and then you pause it, and then you go to your living room television, and then you obviously want the content to play from where you had left off. So there has to be a seamless handover between multiple devices. So this required like instant, I would say, microsecond latency uh, to just pause it and play it on the new device. So we achieved this use case, I would say, through the ScyllaDB model. So the next use case I would like to discuss here is the viewership count. So that's very interesting, and people were really interested on it. So the viewership count could be per user or could be per ID. So we achieved this viewership count through ScyllaDB, and how we achieved is like we have a table which where we used user ID as a partition key and the asset ID as the sort key to generate a view out of it. And then ScyllaDB, interesting thing is that it gives you a TTL like Redis. So we use the TTL of our heartbeat time, which is 60 seconds. And then we use the time window compaction strategy. So it leverages timing window compaction inside the memory, and then it clears out the data after some 60, whatever time to live you give. So we leveraged, and so this table is being populated on every heartbeat from every front end, every user, and then it's automatically cleared with the TTL and Scylla. So we could achieve getting this viewership count from Scylla. Okay, so the next slide you see is our load test report. So you as you see that there are 41.7K requests per second. So this is one of the load test report which like we were when we were deciding which database to use. This is one of the benchmark reports there. So even with such a high throughput, we could achieve a microsecond write latency and an average microsecond read latency. So this really helped us to decide, as you can see, to get a clear view of what Scylla can do. Okay, so with the next slide, I'll share some interesting facts about our system. So you can see the total size of our ScyllaDB is around 9 TB. So even with such a large volume of data, it's able to handle latencies within microsecond and a single digit millisecond. So which is quite huge and which is quite tremendous. Second thing I would like to quote is we get a daily peak concurrent viewership count of 1 million. So you can see per second we are writing so much data into Scylla and getting so much data. Okay. And the third thing I would quote some interesting factors. We process around greater than 100 billion heartbeats in a day. So that's quite huge. So I would like to share some learnings about Scylla. What during the course of our design and development, we learned some things which might help you. So data modeling, I would say, is the key factor to achieve these single-digit latencies in ScyllaDB. So your data model should be proper and okay. So second thing is like you should use the right quorum and compaction strategies. So I would give you an example like, do I want my heartbeat to go into every node before I read it? So, or I can just survive with a local quorum. So you have to choose the right quorum so that you achieve the right latency with the right SLA. So, and then you have to choose your partition and clustering keys wisely because it's not easy to modify them. So it should satisfy your use cases. You can use materialized use for faster lookup. That's so always avoid using filter queries. So if you filter and you go across partitions, Scylla will not be a good use case here. Avoid We should avoid non-prepared statements. All should be prepared statements. So, and use async queries for faster querying, processing. So Scylla helps you to use async queries. So if you we are shooting, like I showed you the metadata model where we are shooting 20 sync queries to get 20 metadata. So Scylla is able to handle even that in milliseconds. And another good learning which I would share here is there is Scylla zone aware clients. So you don't have to go to across AZs to get your data. So if you go across AZ, there is a network cost associated with it. So this helped us to save a lot of network cost. Okay, so lastly, I would say let's stay in touch. We have given our email IDs and our LinkedIn profile IDs there. So let us stay in touch, and we are always there to if you need any assistance or anything. So we are always there to connect. Thank you.